Hey there, and welcome to Unit 6 on exponential and logarithmic functions. Make sure you download these notes into your OneNote if you've been keeping your notes there. Otherwise, make sure you're copying your notes that you need for this section. This is 6.1 on graphing exponential functions. The objectives in this section are that you will be able to graph exponential growth and exponential decay functions, and it falls under these two standards, FIF 7, and it's dealing with the key features of graphs, which are including exponentials, and FBF 3 describing the transformations of functions, and so that's what we're looking at in this section today. So let's look at a couple of key terms that we need to look at first, a couple of things that you may have seen in Algebra 1, but just reiterating it here. Remember that an exponential function is any function where the base is the constant and the exponent is the independent variable. In this example, like y equals 3 to the x power. This is an exponential function. We're used to power functions where the variable is the base and we have a power like squared or cubed for that exponent. Now, exponential functions are a little weird. We're going to look at the graph in a second, but an exponential function has what we call an asymptote. And this asymptote is a line that the graph will approach as it goes to either positive or negative infinity. And as we get up into pre-calculus and calculus, for those that are going to those courses next year, that's what we're going to talk more about, is asymptotes of certain graphs. Had we gotten to some later units, we would have talked about sine, cosine, and tangent functions as our trig functions, and the tangent function actually has multiple asymptotes that we will talk about. Now, there's two types of functions like we talked about in the objective, an exponential growth function and an exponential decay function. We're going to start with growth for the first half of this lesson, and we'll look at decay in the second half. Now, an exponential growth function is any function that can be written in the form f of x is equal to b to the x such that the b is greater than 1. Now, why is it exponential growth? Well, look at the graph that I have over to the right here. As this graph goes from left to right, what is happening to the graph? It is what? Growing. It's going up. And so that's what we're looking at when we look at exponential growth. And when we look at exponential decay, that will reverse, right? So as we go from left to right, this graph will go down. So let's look at some of the key characteristics of the parent function of exponential growth functions. Like we said before, b to the x, where b is greater than 1. These functions are continuous. They are one-to-one, which means their inverses would also be a function. And as we go from left to right, the graph is, as we said, increasing, right? The domain of exponential functions is all real numbers, and the range is related to the asymptote. Now, the asymptote, like we said, is a line where the graph is going to trend towards it as we go very far out. Because what's going to happen is this red line, this line here, is not going to cross the x-axis, but it's going to get ever closer and closer and closer to that y-axis, so close that we can't even tell that it's not touching. But if we actually were to look at the values to multiple decimal places, we would see that it is not exactly 0, but it would be like 0.000000001 something, right? It would be very close to 0. And for all purposes, it could be 0, but it's actually not. This graph will never touch the x-axis. And so the asymptote of this is y equals 0, and so that is the x-axis. And the range is related to that because this graph will be above this x-axis in this case. There is one intercept, and it is the y-intercept at 0, 1. Its symmetry is none. This does not reflect anywhere. It doesn't have point symmetry. And there are no extremes because this graph is always increasing. There is no change in increasing or decreasing. Okay, so let's look at how to graph these. And we're going to look at this case here. Y is equal to 2.5 to the x. And we want to state the domain of the range and the asymptote. Now, the asymptote is going to be the easy part. The asymptote is the x-axis here. So this graph is not going to cross this x-axis. The y-intercept we said was what? What is the y-intercept of regular exponential growth functions? The y-intercept is 1. So this graph is going to go through at 1. Now, let's talk about a couple of other points I didn't mention previously. We have 1b and negative 1 and 1 over b. Now, what that means is this. When I go to my table, and I have my x values and I have my y values, right? my x values, let's go -2, -1, 0, 1, and 2. Watch what happens with these points here. And I plug this into 2.5 to the x. Well, 2.5 to the 0 is equal to what? Remember that anything to the 0 power is equal to 1. Hence why that y-intercept is at 1. And remember that anything to the first power is itself. So I'm going to get 1 and 2.5. So I'm going to get a point there. And then for 2, remember we're going to get 2.5 squared. So what is 2.5 times 2.5? Now, some of you want to throw out some crazy numbers, but it's actually 6.25. Because what is 25 squared? 25 squared is 625. And so I'm going to get 2 and 6.25 right there. And so I start to see this exponential growth function going up like this. And so let's talk about the other half. Because again, this isn't going to be a parabola, so I'm going to go back up this way, right? When I do 2.5 to the negative first power, remember that means that I'm going to do 1 over 2.5. And so what is 1 divided by 2.5? When we do that division, we get 0.4. It is 4/10. And so I'm going to be at -1 and 4/10. I'm going to be just under a half. And when I do that for -2, that means I'm going to get the 1 over this 2.5 squared, so that's going to be 1 over 6.25. Well, 1/6 is about 0.16 repeating, and so this is going to be even smaller than that. And so when we do 1 divided by 6.25, we actually get exactly 0.16. And so this is going to be even closer to my x-axis. And if I were to go to -3 or -4 or -5, this would continue to get closer and closer, but it would never cross. This will come out like so. And so these are my y values. And so this is the graph. The blue is the graph. And so what is the domain? Well, the domain, of course, is all real numbers. -infinity to +infinity. The range is y greater than 0. It is not greater than or equal to 0. This graph will never have a y value of 0. So don't put greater than or equal to here. It is just greater than. And so this would be from 0 to infinity. Now pay attention. This is parenthesis here, not bracket. Because remember, if it's equal to, it's a bracket. If it's not equal to, it's a parenthesis. Okay? And so where's the asymptote? That's the last thing it asks for. Where's the asymptote? The red line is y equals 0. And so that's it for the graph. So let's go and look at example 2. In this problem, we're going to be looking at transformations. And the transformations just mean the same things that they've meant the entire time. And if you go back to chapter 2, this is where you're going to talk about the A, the H, and the K, right? Remember that the A is our vertical dilation and our reflection. If we've got a negative sitting out front, that's going to reflect it across the x-axis. That A value, being something other than 1, will give this a value that will either stretch or shrink it vertically. So again, it's going to multiply all those y values by that factor. Remember, the h is the horizontal transformation, and remember the h lies to you because it says x minus the h, and then plus the k out back. And so let's look at example 2 and see what we get out of it. And so we got f of x equal to 2 times 3, x plus 1 minus 4. So let's talk about the transformations and also talk about what parent function I'm looking at. And we're going to graph that parent function first, and then we'll deal with the transformations. Think about what is the b value. The b value is going to be the number that's typically inside the parentheses when we've got a whole bunch of these transformations. So again, I'm going to originally be going through at 0, 1, and then I would be at 1, 3. And what is 3 squared? Well, 3 squared is 9, so I'd be up here, right? And we can reverse those points, and I would get 1/3 and then 1/9, and the graph would continue the other way. And so again, we could list the original. This is just going to be 3 to the x, and so I'm going to get -2 and 1/9, -1 and 1/3, 0, 1, 1, 3, and 2, 9. But I've got 3 different transformations happening in this problem. And that's it. What it asks us to do here is identify them. So the first transformation is that this will be a vertical dilation by what factor? That's the 2 in front. So all of my y values will get multiplied by 2. Vertical dilation by a factor of 2. And so if I do that, watch what happens to my table. So I'm going to get 2 times 3 to the x. So now I'm going to have 2 ninths, 2 thirds, 2, 6, and 18. And so all these points will just double on themselves, right? So this point's here, this point's here, this one's now up here, and this one's off my graph. And then I'm going to take all those points and deal with the two transformations from there. And so I'm going to have a horizontal translation. Which direction? Is this going to go to the left or go to the right? It says +1. So plus normally means it goes to the right, but remember the x lies to you, so it's really going to go to the left 1 unit. And the -4 out back, that's my vertical translation. And my vertical translation says -4, so that's going to go down 4 units. And so I'm going to take all those red dots, and I'm going to move them 1 left and 4 down. And so this point's going to go 1 left and 4 down, so 1, 2, 3, 4 ends me up here. 1 left, 4 down is going to end me up right here. 1 left and 4 down ends me up here. And this red dot, 1 left and 4 down, will end me up here. Now the other thing that also transformed is our asymptote. Our asymptote originally, I'm going to put it in blue here, or purple, sorry. Our asymptote originally was the x-axis. Now, multiplying that y equals 0 by 2 is still going to give me 0. Moving a horizontal line left does nothing. And moving it vertically means that my line is also going to shift down 4 units. So my asymptote also shifts down with this graph. And so what I'm going to get is this. And again, this point here would have been at 18, so it comes left and it'd be at now 14, so it'd be way up here. And so it's going to come way up like this. And so it has to state the domain, the range, and the asymptote. And so what's the domain? All real numbers, it hasn't changed. Negative infinity to infinity. The range has changed. And again, remember that your range is based on the asymptote. Where did the asymptote end up? It's at y equals -4 because it got shifted where? Down 4. And so it means my range is y is greater than -4 or -4 to infinity with a parenthesis on both ends. And so that's the difference with these. And again, there's different methods you could use to get these transformations figured out. But I personally feel that if you do the vertical dilation first and then you shift for the two translations, that's going to be the quickest way to get these points where they need to be. So let's look at example 3, graphing exponential growth functions. And so in 2006, there were 1,020,000,000 people, or 1.02 billion, worldwide using the internet. At the same time, the number of users was growing at 19.5% annually. Draw a graph and show the number of users, how they would grow from 2006 to 2016 if the rate continued. And so let's talk about what function we're going to write here. Now, I could use all these decimal points here, but you see I've written this as 1.02 billion. And I'm doing that for the sake of understanding that we can shrink our graphs down and not have to graph into the billions. And so what I'm going to write here is y equals. Now, let me talk about what do the a and the b in our functions represent. The b is our growth factor. And sometimes you'll see the letter r used here. And remember that our growth factor in an exponential growth function has to be greater than 1. And so we're going to talk about how we get that in a second. The a value, remember, is our vertical dilation, right? But the a itself is the initial value when we deal with word problems. And so my initial value in this problem is that y is going to be equal to 1.02. And again, I'm scaling this down so I'm not having to write 1,020,000,000 and all those zeros, right? Now, what is my growth factor? if this had no growth, right? If this was to say today, 1.02 billion had internet, nobody else gets internet, right? I would multiply this by 1, right? Because it would never grow. But this has to be greater than 1, right? But my growth rate is at 19.5%. But I don't have the growth rate, I have the growth factor. And what that entails is 1 plus the R. Okay? Now the R is this percentage. So this is my R. But I need to change that percent to a what? Decimal. So I'm going to write that y is equal to 1.02, 1.195, because remember we're going to move that decimal twice to get it to a decimal, to the x. And so I've done this graph on Desmos, and so I'm going to put that on the screen now. And so here's that picture. So again, my 1.02, so you'll see that I'm just above 1. It's hard to tell on this picture, but I am. And then it is growing at a rate of 19.5% each year. And so you'll see that my x is labeled as year since 2006. So 5 would represent the year 2011, and 10 would represent the year 2016. And you'll see that these are people in billions with internet. Now, let's pay attention to what values we have here. We could be asked a whole bunch of things for this graph, right? So it's going to start here, that's a 0, and it's actually going to end right here. Do I need this piece? No, this piece doesn't make any sense. Because for one thing, you know, if 10 is 2016, so this is 2017, 2018, in 2018, do we have 8 billion people on the earth? Not quite yet. So this model doesn't fit when we get past 2016. And of course, does the model fit for before it starts in 2006? It might, but it's not a guarantee either. Again, this model works for the years 2006 to 2016. Now, we're going to see when we do example 5 in a second that we can be asked multiple things from this. You know, we can be asked when does it reach 4 billion people, or in the year 2010, how many people would this estimate out to having internet? And all those questions we could derive from the graph. So let's flip the script and look at exponential decay. Now, you might be thinking that exponential decay would be where the b value is negative, but it's not. Because here's the thing. Remember that you cannot take a negative number to a power and get a consistent function. Because think about if I take like -2 and I raise it to the first, right? I would get -2. But then I take -2 to the second and I would get +4, right? And then I would take -2 to the third and I would get -8. And so we see these signs keep going back and forth. And so exponential growth and exponential decay, our base has to be positive for exponential functions. So if we go all the way back up to the top of our definition, for an exponential function, going back to this first definition, the base must be that b is greater than 0. And also the b cannot be equal to 1. Because again, if the b is equal to 1, then it's not exponential, it's just constant. Alright, so getting back to exponential decay here. You'll see that this function is very similar to its brother, the growth function, right? Except instead of it being really low at the start and then growing, we're starting high and shrinking. And the only change that really happens is what my b value can be, and then what happens with these supplementary points here. It's still that it's 1 comma b, right? But now my b is smaller than 1, so it's going to be closer to the x-axis. Everything else down the list stays the same. Our asymptote's still at y equals 0. Our asymptote is still the x-axis coming across here. Our intercept's still at 0, 1. There's no symmetry, there's no extrema, right? Our range is still y is greater than 0. So let's look at graphing an exponential decay function. The transformations work the same way, but I'm just going to do a simple exponential decay function. Transformations would do the exact same thing that we just did in example 2. Okay, so y is equal to 1/4 x. So think about the values here, right? Again, there's no transformation, so the y-intercept is going to be at 1. When I plug in 1 to this x, I'm going to get 1/4. And when I plug in -1, right, so if I've got my x's, -2, -1, 0, 1, and 2, this is 1, this is a 4th, 1/4 squared is going to be 1/16. And so when I do -1, it's going to flip this fraction. So I get 4. And when I do -2, I'm going to flip this fraction and get 16. Remember, it's not going to make it negative. It's going to make it a bigger number because we're taking a fraction and flipping it. And so, again, this value would be off the screen. This one is here, there, and then this one is here. With that asymptote at the x-axis. Okay, so again, that's our function. What's the domain? As for any exponential, it's all real numbers. The range is y is greater than 0, 0 to infinity. And our asymptote is where? Y equals 0. All right, let's take a look at the last question that we have, another word problem here for example 5. The pressure of the atmosphere is 14.7 pounds per square inch at the Earth's surface, and it decreases by 20% for each mile of altitude up to 50 miles. Wants us to draw a graph to represent the atmospheric pressure from 0 to 50 miles and estimate the atmospheric pressure at an altitude of 10 miles. And so again, we've got to think about what function am I going to write here. Remember, so a times b to the x, right? There's no transformations happening here. Remember, a is your initial value. So y is equal to what? Well, what's my initial value? At the surface of the Earth, it's 14.7 pounds per square inch. Now the question becomes the b. This b, when we are dealing with a decay function, becomes our decay factor. And our decay factor is going to be 1 minus the r. Remember, because for growth factor is 1 plus the rate, right? And so we're going to get y is equal to 14.7. And then we're going to get 1 minus, what's it decreasing by? 20%. So I'm going to get minus 0.2 here. So y is equal to 14.7 times 0.8 to the x. And that's where we're on our graph. And again, I'm going to go to Desmos and plot that graph on the screen. And so here's our graph. And so we see that it's going to cross up here at 14.7 and begin to decay as we go down to the right, because again, it's a decay function, right? And so the question asks us to draw it. And so again, this is where more complicated cases we'll use technology, right? And it says to estimate the atmospheric pressure at an altitude of 10 miles. Well, at 10 miles, we're sitting here, and each of these are by 1. And so at 10 miles, maybe 10 comma what? Well, it's a little less than 2, maybe like 1.6. Now, if we really want to figure this out, we could plug this into the function. We can go y is equal to 14.7 times the 0.8 to the 10th, and do that in our calculator. And when we do that in our calculator, we're going to get y is equal to 1.578, so on. And again, think about what our y is in. This is y is equal to 1.578 pounds per square inch of atmospheric pressure. And so this is why the higher altitude you get, the thinner the air gets, right? So think about going to just even 1 mile up, right? So at 1 mile, we're sitting here. Well, if we're normally used to 14.7 pounds per square inch here in the Midlands, right? If we go to Denver, that air is 20% thinner, right? Because we went from almost 15 down to 12, basically. It's 20% thinner, and that's what our rate was, right? 20%. And if we go to 2 miles up, right? So 10,000 feet. Now we're sitting at under 10. And so it's 20% and then another 20% of that. Again, it's not 40% because, again, you wouldn't lose 100% at 5 miles, right? At 5 miles, you're under 4, but you've only lost about 60+% at that point, okay? So again, we could see this is our picture here. And again, atmospherically speaking, that above 50 miles, you lose it at a quicker rate at that point of what's left because you're getting closer and closer to space. So with that being said, this is exponential growth and decay. The word of the day was in your announcement video today, so I hope you watched your announcement video. but I will repeat it here. So may the 4th be with you. That is your word of the day, because Star Wars, right? So again, if you have any questions, hit up the Zoom, not the Zoom, but the Google Meets. And I hope y'all have a great day. Stay safe, stay home, and don't do anything stupid, y'all.